Our last video in Chapter 8 is on bond dissociation energies. Bond dissociation energies are another way to calculate the delta H of a reaction. And after this, we will have 3 total ways to calculate delta H of a reaction. The first way was using Hess's law. The second way was using the standard enthalpies of formation of reactants and products. And this will be using the energy required to break or form a bond. In a chemical reaction, reactant bonds are broken and product bonds are formed. Table 8.3 in our textbook shows the average bond dissociation energies. And what Table 8.3 does is it gives us particular bonds, whether they are hydrogen-hydrogen bonds or hydrogen-carbon bonds. It gives us a whole bunch of different bonds, and then the value that's next to them is the amount of energy in kilojoules per mole. Because reactant bonds are broken, and to break a bond that requires the input of energy, these bond dissociation energies tell us how much energy needs to be input to break a reactant bond. And so reactants have a positive bond dissociation energy, meaning they are endothermic. And the bond dissociation energy also tells us how much energy is released when a new bond is formed. And so products are exothermic. Product bonds are exothermic and reactant bonds are endothermic. With these bond dissociation energies, what we can interpret is that no matter what compound these bonds are in, on average it will require the same amount of energy to break or form that type of bond. Looking at our carbon-hydrogen bond, for instance, again, the value of 410 kilojoules per mole means that anywhere we see a carbon-hydrogen bond, whether that bond is in butane or whether that bond is in ethanol, it will require on average 410 kilojoules per mole to break or form that bond. Another thing to notice is that multiple covalent bonds, like the carbon-carbon double bond or the carbon-carbon triple bond, are stronger than single covalent bonds, and triple bonds are stronger than double bonds. And that strength is shown as an increasing value in kilojoules per mole to break that bond, or an increasing amount of energy that's released to form that bond. The more energy that's released when that bond is formed, the more stable that bond would be. Now, we would use the bond dissociation energies, the BDE, to calculate the enthalpy change of the entire reaction, the delta H naught. The delta H naught of the reaction is the sum of the bond dissociation energy of reactant bonds, and from that we would subtract the sum of the bond dissociation energy of product bonds. And we have reactant bonds first because the energy goes in to break the reactant bonds, and we subtract from that the energy of the product bonds because that's the energy that is released. And so the way this equation is set up reflects the endothermic nature of reactant bonds and the exothermic nature of product bonds. Let's do an example. And examples like this will cause you to tap into your knowledge of drawing electron dot structures. We need to use bond dissociation energies to determine the enthalpy change of the following reaction. We have propane plus 5O2 gives us carbon dioxide and water. Now we'll need to figure out how many and what type of bonds we have. Propane is this molecule. We have C bonded to carbon, carbon bonded to carbon, and there are 3 carbons in a row. And then the 2 end carbons are bonded to 3 hydrogens. The middle carbon is bonded to 2 hydrogens. And again, the standard enthalpies of formation and the bond dissociation energies are not something you'll need to memorize. You'll just need to know how to use them when given these values. But for standard energies of formation, you will need to know which types of reactants or products have a delta H naught sub F of 0. Alright, so I've written 5O2. Oxygen is a diatomic molecule, and the oxygen has a double bond. Carbon dioxide, carbon's in the middle, and it's double bonded to oxygen on both sides. And we also have 4 water molecules. Each water molecule is oxygen bonded to 2 hydrogens. It's important to know that when using the bond dissociation energies, the values that are given in the tables are written for bonds in the gas phase. We have all gas phase reactants and products here, so we don't have to change them. But if you have a solid or a liquid, you cannot use the bond dissociation energies for that compound. You would have to first convert it to a gas using the delta H of vaporization. Now, from this information, it looks like we have the following types of bonds. We have 3 carbon-carbon bonds. We have, oops, no, we don't have 3. We have 2 carbon-carbon bonds, right, because this is 1 and this is 2, so be careful with that. I should tell myself that. 2 carbon-carbon bonds. And then we have 8 carbon-hydrogen bonds. And then in our O2 molecule, one O2 molecule has 1 oxygen-oxygen double bond, but we have 5 total of them, so we have 5 oxygen-oxygen double bonds. So here we're counting up how many of each type of bond we have. And we have to multiply how many of that type of bond by the bond dissociation energy when calculating the delta H of the reaction. These are our reactants. On our products, we have 3 moles of carbon dioxide. Every one has 2 carbon-oxygen double bonds, and so that 2 times 3 is 6 total carbon-oxygen double bonds. We have 4 waters. Each has 2 OH bonds, and so that means we have a total of 8 oxygen-hydrogen bonds. So here is how many and what type of bond we have. 2 carbon-carbon bonds, 8 carbon-hydrogen bonds, 5 oxygen-oxygen double bonds, 6 oxygen-carbon double bonds, and 8 oxygen-hydrogen single bonds. Now at this point you would want to look up the values for the bond dissociation energy of each type of bond. I've already done that and summarized it here. And so here are our number and types of bonds again, and their bond dissociation energies. And notice for each energy, this is the energy of one of those bonds. We have to multiply it by the total number of bonds. And so what we'll do is take our sum of our bond dissociation energies of our reactants. We will do 2, and that is 2 moles of that bond, times the 347 kilojoules per mole. This is for our carbon-carbon bond. And then to that we'll add our 5 moles of oxygen-oxygen double bonds and multiply that by the BDE of an OO double bond, 498 kilojoules per mole. And then to that we'll add our 8 moles of carbon-hydrogen bonds by their bond dissociation energy, 413 kilojoules per mole. These are all of our reactants now. So we will do our multiplication and then add them up. And from this we want to subtract the sum of the bond dissociation energies of our products. We will do 6 moles of carbon-oxygen double bonds, so that's 6 moles times 805 kilojoules per mole. And from that, or to that, we will add our 8 moles of oxygen-hydrogen single bonds, 464 kilojoules per mole. So, on our reactant side, we will have 2 moles times 347 plus 5 moles times 498 plus 8 moles times 413. On our reactant side, we will have 6,488. So our delta H naught of the reaction equals the sum of the bond dissociation energy of our reactants, 6,488 kilojoules, minus the sum of the bond dissociation energy of our products. For finding our products, we'll take 6 times 805 plus 8 times 464, and that gives us 8,542 kilojoules. And so, taking our 6,488 kilojoules minus our 8,542 kilojoules, we will get a delta H naught reaction value of negative 2,054 kilojoules. And that negative sign reflects that our reaction is exothermic. And if you look at what type of reaction it is the combustion of the hydrocarbon propane, and combustion reaction should be exothermic. And so our negative sign for our delta H naught of reaction makes sense.